All right. Hi, everyone. So last time we had kind of talked about the test format, and I gave you a bunch of stuff to work on that had some worked out solution answer key stuff. Do you want to start questions there? Do you want me to talk? I don't know what you need. Tell me what you need. Paul.
So could you go over number 3?
This one?
Yeah, that one.
Sure.
I think I see what he did, but I just want to make sure.
Yeah. So this is one where, depending on how you look at it, you could approach it in a couple of different ways. When I look at this, I see something I can do some sneaky algebra stuff and avoid having to do any complicated calculus. That's where I would prefer to go, personally. But you could use the quotient rule to do this. That's not wrong. What I would recognize here is that I can rewrite 4x, or 4 to the 3x plus 1. 4 is the same as really 2 squared. So if I make an exponent of an exponent, that's the same thing as like 2 to the 6x plus 2. Thank you. Good morning. Everybody okay there? And I'm going to think about this as really two things with a common denominator. And since these are both powers of 2, I can divide these fractions by subtracting the exponent, right? So 2 to the 6x plus 2 minus x becomes 2 to the 5x plus 2. And 2 to the x plus 5 becomes just 2 to the 5th. Because I subtracted the exponent. So x plus 5 minus x is just 5. Now, when I take the derivative of this piece is a chain rule, but that's it. So the outside is 2 to the x, and then the inside is 5x plus 2. And then remember, when we take the derivative of an exponential, you get natural log of the base stuck on there also. And the derivative of 2 to the 5th is 0, because it's a constant. So I'm done. Sophia?
For like the 5 times log to the 2, is the 2 from the base?
Yeah, so the derivative of something like this, that's the derivative rule that I used. So that's where this part and this part come from. And then this is the derivative of the inside from the chain rule.
And then you don't worry about the plus 2, like that's a constant.
Correct. Yes, when I differentiated 5x plus 2, it just turns into 5. All right, exactly. Yep. Paul, does that feel good?
Yeah.
Now, you could have done this with the quotient rule. It's not wrong to do it that way. You're not going to get as neat of an answer tumbling out of it without a lot of work. And it's a little bit more calculus to kind of grind through the chain or the quotient rule, because you have a few more derivatives to take that are a little bit more complicated. But you could do it. It's not wrong. This is the way I would prefer to do it, because the answer I get is very neat when I'm at the end. Victoria? Mhm. So 4, it's a question of, I look at this, initially anyways, and I say, okay, I could do this with a quotient rule, for sure, right? But maybe I could simplify this trig expression into something that's a little bit easier to deal with. That's entirely possible. Maybe I don't recognize that right away. So I would probably start by saying, well, is tan plus cotan over sine just simplify down into like a single trig expression to make this problem pretty easy? Or you could be like, you know what? I don't remember those trig identities well enough right now. I'm just going to quotient rule the heck out of this thing, and that's okay too. I would probably try, because I seem to remember tangent plus cotangent being something. So remember, tangent is sine over cosine, and cotangent is cosine over sine. Everybody's okay with that? So if I add the fractions on top, I would multiply this one by sine x over sine x, and this one by cosine x over cosine x. So what am I going to get in the numerator on the top? Sine squared plus cosine squared. Everybody see that? What's that? 1. So I have that. And if I simplify that, I'm just kind of multiplying by the reciprocal. So I get that, which I guess I could call cosecant squared x times secant x, which isn't great, right? What have I managed to do? I changed this from a quotient rule problem to a product and chain rule problem. Not much of an improvement. So doesn't really matter. It's apparent at this point, right? But the answer either way you're going to go is going to be the same. So if I take the derivative of this, I'd have cosecant squared x times the derivative of secant, which is
minus secant times cotangent?
I think tangent though, right? Everybody's agreed? That's correct. Is it negative? No, it's not. Cosecants are the ones, and cotangents are the ones that spit out the negatives, right? Cosine, cosecant, cotangent, I think all spit the negatives.
But isn't it not a
Yeah.
rule?
No. Then I have the plus. Yep, I'm still got more. You're absolutely right. And then I have secant times the derivative of cosecant squared is a chain rule. So that's going to be times 2 cosecant x, and then the derivative of cosecant is negative cosecant times cotangent. And that's short of a little bit of simplifying where we're going to live. Right, so what do we have here in common? I can take out a cosecant squared, and I can take out a secant. And then that leaves me with tan x minus 2 cotang x. And that's probably as good as you could hope to do with that.
I have a question. Go back to like first of 1 over sine squared. What did you do after that?
This right here,
Yeah.
I just rewrote it as cosecant times secant. Or you could have used, say, taken the where it was, and you could have just kept going, but then you have an additional chain rule that you have to deal with, and still the product. I just rewrote it that way to get rid of the chain rule part. Sophia.
If you were to do the quotient rule,
Probably was going to be easier.
right, would you want to do tan x over sine x, and then like separate it from, and then do plus cotangent over sine x?
You could do it that way. I probably wouldn't, because now you're talking about 2 quotient rules instead of just 1.
So you can do.
You could separate it, though. You could do that. I probably wouldn't bother in this case because you're doing a quotient rule anyways.
Right.
I'd rather just do 1 than 2, even though I might have a sum in the numerator. That's not a big deal, though. But you could do it that way, particularly if you see something like, if it was like sine plus cosine over sine, then yeah, for sure, let's do that. I write it as 1 plus cotangent and just turn it into a quotient rule into a single, cotangent. Like, well, that's an improvement. But yeah, you could do that. I probably wouldn't bother in this problem.
Okay. Thank you.
So hindsight here probably wasn't worth messing around with the identities because what we got back wasn't really any easier to deal with than what we started with. And that'll happen, right? And I can't look at one of these things and know whether there's going to be a giant shortcut or not if it's not like glaringly obvious. In hindsight, Mr. Kulik probably should have put cosecant here, and then things simplify really nicely to just be that all turns into secant, and that's a lot nicer. Mia? Sure. Oh, I need the page. Okay, oops. So it says use implicit differentiation to find the second derivative evaluated when x is equal to 0. So I would start here by just figuring out what y is when x is 0. So if I do that, that piece zeroes out. So I have that. And if I multiply both sides by a -1, I get e to the y equals 1 over e. And you could take like the natural log of both sides. When you do that, you get y is -1. Or you could just eyeball it. I mean, I know e to the -1 is 1 over e. I would recognize that. But if you didn't, just do the natural log of both sides, and the natural log of 1 over e is just -1. You could type that into your calculator. There's no problem doing that. Okay. So I'll just make that a little note there. We okay?
Right.
Is that cool, Sophia?
I just
Oh, why that went away? Yeah, it's because I plugged in the 0 from the problem.
No, makes sense.
Again, easy answer, but like ask if you're not sure, right? All right. So now let's take the derivative of this. So when I take the derivative of x squared y, I need to do the product rule. So that'll be x squared, and the derivative of y is going to be 1, and then a dy dx, I'll just write as y prime. And then the derivative of e to the y is going to be just e to the y, and then a dy dx, I'll write as y prime. And the derivative of constant is just 0. What's up? Oh, yeah, thank you. Yep. Thank you. So there's that. Everybody cool? So if I wanted to, I could get the y prime by itself here. That's probably helpful because I have two product properties I'm looking at on the following step, and that just might be algebraically a little easier to deal with. So when I do that, I'd subtract the 2xy from both sides, factor off the y prime, and then divide by the x squared minus e to the y. So again, I didn't write out the algebra, but I said it orally, what I was doing. If you need me to write it out, I can. But it boils down to just getting the y prime by itself. Now, if I take the derivative again, I'm going to have to do a quotient rule. So I'm going to have the bottom times the derivative of the top.
Wait, why is this y? No. Oh, never mind. I have a question.
Yeah.
So look, on your notes, you found the second derivative using your, like you didn't do the quotient rule.
That's fine. You don't have to do. You could do it that way also. Either.
Because then when it asks like on B to show that answer specifically, you did something with like finding the second derivative equation to find that equation specifically. I don't know.
You can do it either way is the shorthand, Victoria.
Okay.
And oftentimes it's going to be 6 of one, half dozen of the other.
Okay.
Whether you want to do like get the first derivative by itself and then quotient rule it, or just leave it the way it is and like do a bunch of product rules and then do your algebra afterwards. Oftentimes there's going to be no difference in terms of like how complex something gets.
Yeah.
So, yeah, I mean, okay, and then I have the top times the derivative of the bottom. All over the bottom squared. Okay. And now, yes.
So we just need to know that e to the y, the derivative of e to the y is e to the y times y prime. Y whatever.
Yeah, well, I mean, what we're really doing here is you're doing a chain rule, right? So, and then this is just dy dx.
Okay. Thank you.
Yeah, no problem. Still doing okay? At this point, I'm plugging stuff in now. So here, I would plug into the first derivative. X is 0, and y is -1. What is that going to be? But that's easy. That just comes out to be 0. That's nice. And so if I plug in here now, what are we going to get? I'm just going to use the spots down here. So what do we got? We have 2 or negative 2 over e over 1 over e squared.
Where did you get the 1 over?
This 1 over e
Yeah.
is when I plug negative 1 in.
Oh.
So e to the negative 1 is just 1 over e. Right? You could write as e to the negative 1, though. That would be fine.
Oh, why? Well, wait, we made that y was equal to -1.
Uh-huh. We did that at the very beginning, very first step.
Yeah, I thought it was.
And if I simplify this, then I get negative 2 over e times e squared over 1, which is just negative 2e. Is that what I had on the key, I hope? No! Oh, fiddlesticks. What did I put down? Oh, I have y equals to positive 1? Well, that would be a problem, huh? Let's look at what I did here. Oh, yep. That's just a, that ought to do it then, huh? So I think algebra-wise, that's fine, but like obviously when I plugged in y equals 1, everything after that goes... Sorry, guys. Negative 1. 2e? Or negative 2? Was it negative 2e? I forget now even. It was negative 2? Thank you. I'm not going to obviously fix all the other places where there's a problem because I don't want to spend 10 minutes like going through and changing all the 1s to negative 1s or whatever, but yeah, of course. So yeah, all we would be doing is here at part B, instead of plugging in the values at this step, I'm going to plug in that second derivative everywhere where or that first derivative wherever I had the y prime. All I'm doing is I'm taking this, and wherever I see a y prime, I'm just plugging in the equation for the first derivative that we found earlier.
Okay. Right, I get it.
It's okay with that. Which is kind of yucky looking. Kinda, Mr. Kulik? Okay. very yucky looking. Well, that's what the problem asks us to show, that this thing is equal to that.
It's equal to. Oh, can we just say we have to?
We got algebra it. Well, then what's the point of me putting it on there? I'm trying to be helpful and like, here, you don't have to simplify unlimitedly. This is what I need you to get to. Just give me the algebra. So I'm going to multiply the top and bottom by this so that I can clear the fraction. So if I distribute, I need to distribute 1 to here, 1 to here, 1 to here, and then 1 to there. Okay? So when I do that, this stuff is just going to become 4x squared y. And then I'll have the minus 2y times and then this stuff is just going to multiply together. That's okay. Go ahead.
So why didn't you distribute the x squared minus e for y to the like the first part?
Because it's multiplication between them.
So,
so this is all like, this is all one thing, right? So I'm just going to distribute either to the first thing or the second thing. The second thing is where the fraction is, so that's why I'm distributing it only into that part. Does that feel okay? And that's probably easier initially than like trying to FOIL all this stuff out, right? Or distribute all this stuff out. Like it was going to get pretty gross and pretty messy, and I just... Okay. So then what do we have here? I'm going to do the inner stuff next. So let's just distribute that stuff through. And hey, that's pretty nice. Look, we have a common factor there, so we can combine some like terms here. And we'll do the same thing there. Okay, and notice that this stuff is just positive 2x squared y. So now that has to FOIL, but this one I can just distribute, which is, that's a relief.
two Y's.
I added the exponents. So like when I multiplied this thing to there,
Oh, okay.
e to the y times e to the y is e to the y plus y,
Gotcha.
e to the 2y. No, this is the end of the road right now. We're just combining some like terms now.
Oh, I know.
So those guys got a +1 and a -1. Those will cancel out. These guys can add together. That'll give me a 6 of those. And then everything else is not a like term, right? So I think that's all the rest of them, and I think that's what we wanted, right? If I go back and look, I think that's it.
I don't. I was so.
It was annoying, and it's tedious, and there's lots of places to like make a silly mistake.
I think the problem is just like convincing my brain that that's what I have to do, because I feel like my brain will go somewhere and then I'll be like, no, that doesn't look right, and then I'll just like try again.
In fairness, the one that I wrote for you guys for the test is much easier than this.
Oh, okay. Yeah, I was gonna say there's no way I was figuring it out.
But isn't this the logarithm? Everything he did make.
Well, no, this was the
Yeah, we're not using logarithms.
no, we're not doing that one.
Okay. So this would,
Yeah.
okay.
Well, no, this is B that we just did.
Oh.
That's what we were trying to do. Justin?
So for the, you got 2y, e to the 2y, but in the answer, it's 2, it doesn't have that y.
Oh, I mean,
I got the same thing as you, like the answer.
right here.
Yeah.
Okay.
The answer doesn't.
That's probably again. That's probably my mistake.
What did he ask?
Justin is saying that my answer key doesn't have this y here, and it probably should have.
Oh, yeah.
Again, my apologies. My deepest, sincerest apologies. Okay, we have like 4 hands up at the one time. I want to answer all. I want to address all of these things. I just want to. We all talking about this problem.
Oh, no. I thought we were done with this problem.
Why does it exist? I thought this was supposed to match the one above.
It was.
What?
Because the other one had an A.
Oh, no, I see how there can be a problem.
Is that just like less?
Like, you said to show that.
Right. Okay. So what am I missing here? What are you saying I'm missing?
Well,
This piece?
Yeah. I think yes.
Okay. Let's go back and check then. Okay. So it is having to do with this stuff going the wrong way and then not canceling out. Okay. So let's double check here. Let's go look at what I did. Yeah. Boy, that was just for the record, it was quite a bit nicer to have done it the other way, huh?
Yeah, that's why I was like saying we got on your you didn't do like
That's why you just have to
Like, how did you do it that way?
Do it what? The way that I just did? Or I did on the...
Like, do it the way on there. Because you took your equation from before, like substituting out the first derivative, and then you added a second derivative onto that. And then from there you found this.
Okay. So all I did here
Yeah.
was I just then differentiated again. So this was the chain rule, or the product rule from this piece.
Please excuse this interruption. Any freshman who needs a picture retake,
Sure.
freshmen who need a picture retake, please come to the library now. Any freshman that needs a picture retake, please come to the library now.
So each of those was a product. So for example, the first one would be x squared, and then
Right.
the derivative of y prime. And then I would have the derivative of x squared times y prime.
Okay. Wait, why did you put a prime on the x?
Well, because I didn't do the derivative. I'm just saying, I'm just like setting up the product property for you, because you said you wanted me to show that.
Yeah.
Why is that extra one there? Is that a...
I think that's why.
Yeah, I think that's a mistake. Yeah. Yeah. So that's probably why things got mucked up after that. So I think the answer that we have on the other sheet is probably correct.
Okay.
And I think that's probably why my answer has got that extra factor that's too big or whatever, because I have an extra factor of the second derivative floating, or the first derivative floating around in there.
That first equation and find the second derivative by doing, and then. Is that just simple?
Yeah, that's fine.
Well, what do you?
And then I rearranged this as to a first derivative, and you could do the quotient rule on that, or you could,
And plug that into the equation with one.
that would end up giving you the same thing as like this would have, just depending on which way you wanted to go about doing it. Should give you the same result. Okay. I promise you the one that I wrote for you guys isn't nearly this gross. Like I would say it's like 6 of one, half dozen of the other. It's like whatever you feel more comfortable doing. Like, I don't think that it's going to be one of these situations where like one way makes it massively easier than the other. And if it is, it's going to be like you probably wouldn't be able to recognize it from the start that was going to be what you'd want to do anyways, unfortunately. Okay. Sergio.
Does this have to be about this question?
No, I think we've cleared up.
So a little change of pace
Anyways.
from like the actual hard question. I know this is really easy. I just was confused how you got 7/2 and number 1.
On number 1?
Yeah.
Sure. So what I did is I thought about this as thought about it this way.
Yeah.
And I remember that a radical is the same thing as a fractional exponent. So a square root is the same thing as to 1/2. And then I can multiply these guys together. So 2 plus 3/2 is like 3.5, right? 2 plus 1.5 is 3.5,
Yeah.
Yeah.
which is 7/2.
Okay. And then
You didn't show that. That makes sense. Okay.
Okay.
So,
And you're good from here then, right?
yeah.
Okay. Taylor, you had a hand earlier.
I just had a basic question. Alright, so 3.6 is not on the test?
The logarithmic differentiation. The only thing from that section that I would say is necessary is this derivative rule, that the derivative of the natural log is 1/x, which was on the Quizlet,
Yeah.
and that's the only thing that I will appear from 3.6 is that derivative rule.
Okay, this 3.6, I was trying to do the homework and I just had no idea what was going on.
The hard part about the logarithmic differentiation is going to be the cleanup at the end to get the answer in the back of the book.
Yeah.
We can, but let's wait
Okay.
until after the test.
Okay.
Or you can come back during commute time. I'd be happy to do it with you individually, but I don't want to put everybody else through that for something that's not going to appear on the test right now. But I'm absolutely would love to do some examples and work through some of them, but just I think this is not the right time. If that makes sense to you?
Yeah, that was.
Okay. Mia,
I was like, I'm really good at this.
6. Sure. So for 6, this looks terrible, right?
Yeah.
But I can do this with 3 individual chain rules. That's it. Not linked chains, but just 3 individual chain rules. Because when I see this, when I see the natural log around something, I'm immediately going to start thinking back to my logarithm rules. So I can use the power property for logarithms, and an exponent inside the logarithm can become a coefficient. Oops. Now, if you went at this problem and tried doing it as like a bunch of linked chains, you can do that. It's okay. Everybody's okay with what I did there? Now I see that I have a quotient inside my logarithm. So I would use the quotient property here. Actually, let's just write it this way.
Well, I have a question.
Yeah.
Why is a -3 in front of the natural log in the parentheses?
So remember we had this property of logs.
Yeah, I know.
So that's why this is moving to the front. I'm doing no calculus yet. This is all just algebra. Does that feel better?
You're not doing any calculus.
I haven't done any calculus yet.
But isn't that a power rule?
So what I'm using is a property of logarithms. That's the power property for logarithms, not the power rule for differentiation. I know. Mathematicians, you picked some dumb names for things because you're reusing all these. No.
Like if there's ever. Oh yeah.
Oh,
So I'm just using my properties for logs.
oh yes, yeah.
Why did you
Okay.
when we were the -3 log
Mhm.
to the second?
Okay. Sure. You want to write it this way first and then distribute? Is that better?
Wait, is that a quotient?
All I've done is a property for logs. I did the quotient property for logs. Right? Okay. So now I can distribute the -3 through, which I wanted to do before. And now I'm going to do my calculus step. So this is a single chain rule. So it's just the derivative of the outside is 1 over x, but
Because the derivative or the outside is limit x
is the natural log.
or log x.
Yep. And then the derivative of the inside and then the same rule applies here.
Why wouldn't your 3 be negative?
Because it was minus a negative. So this is what we had initially.
Yeah, right. Sorry.
That's okay. And then it's just like a little bit of cleanup if you want it, right? So like I could multiply this stuff together and put it in the numerator. What is that, 72? And then multiply these guys together. And that's as far as I would go, simplifying. I wouldn't make a common denominator there or anything. Because that looks like a nightmare to do.
So for this, for the logarithms, these are dividing, so we make them subtract. So if it's like two things multiplied,
Yes.
is that?
So this was that's the other property of logs. So those are your 3 property of logs.
Yeah.
And you can use those, if you want, to make a problem like this a little bit easier. Notice that the algebra here was pretty easy once you saw what to do. And then it turned it into a pretty easy calculus problem where you just had 2 individual chain rules that weren't difficult chain rules.
So I can make any quotient rule into that.
If you have the log of a quotient, then yes. If you just have a quotient, no. That's what logarithmic differentiation is going to be about when we do 3/6.
Okay. So only if there's a.
Did you just use algebra to get it to where you wanted to?
Well, you start off by taking the log of both sides, so you can use the log properties, then do your differentiation, but you have to like do a correction factor because now you have a dy dx times 1 over y, so you have to multiply the original back through, and it kind of makes a little bit of a mess. This problem didn't have to do that because the log was already there.
Okay, so if the log's already there, you can just kind of throw a log there for that and then do the calculus.
Yeah. Yeah.
So you did the chain rule for the -3.
No. The -3 is just from the power property for logarithms.
Oh, okay.
There's no calculus happens until I get to here. That's when I start doing my calculus.
And what rules did you use for that?
Just the chain rule, and then the
On the
natural log of stuff.
Oh, right. Okay.
So it's just derivative of the outside times derivative of the inside. Right? Mia.
No, it's actually a general question. So like, when we're finding like the derivatives stuff, are those the ones where you would let us simplify and then have to simplify for like the second derivatives, or
So the problems will be stated, the directions will be one of 2 ways. It'll be take the derivative and when the calculus is done, you're done. or it'll be show that this derivative is equal to this. So I will either tell you what the answer is and ask you to fill the algebra in between, or just do the calculus part and stop. That'll be the two types of questions. Which one do you think there's going to be more of? Just do the calculus and stops. Yeah, I think I have, I don't remember if it's 2 or 3 show questions, but that's it. Okay. So there, it should not be bad. Mackenzie. Sure, that was the other page we haven't looked at yet. Is that right? I think it was. All right. So 11a says use implicit differentiation to show that blah, 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 blah. So I'm just going to start by starting with calculus, right? So derivative of this, 6x squared. Nothing complicated going on there, right? Derivative of this requires product property. So 3x times 2y, and then I guess I'll do dy dx since the problem is using that note, or my directions use that notation. Then minus 3, and then derivative of x is just 1, and then we have the y squared. And then the last piece here is just a power property. Everybody feel okay? So just, I did the power property, making 21y squared, and then have the dy dx at the end, because it was a y instead of an x. Is that okay? What I'm going to do is I'm going to take all the pieces that don't have a dy dx and move them to the other side. So that's going to be adding 3y squared and then subtracting 6x squared. And the pieces that do have the dy dx, I'm going to factor those off, that dy dx off. So that's going to be 21y squared minus 6xy. And then I'll just divide both sides by that 21y squared minus 6xy. And I notice that each of those things contains a factor of 3. So if I reduce that, I get y squared minus 2x squared over 7y squared minus 2xy. And that's what I need. That's about the level of difficulty the show prompts are.
Really?
Yeah, they're not horrific.
Oh, that's great. That my day.
Yeah.
And then are the calculus problems a little more in depth?
The calculus problems, like I said before, the way I have it set up, when we talked last time,
I accept it.
what did I wrote this down, didn't we? Oh, it's on this sheet. So like 3 questions where we ask you to find the derivative and no chain product or quotient rules are necessary. You could, although you could use them if you don't see the algebraic way to simplify it, right? Like we saw a couple on there that I didn't have to use any of those because I did algebra to get around having to do it. But if you didn't see the algebra,
So we are allowed to use
yeah,
products.
yeah, you could.
Can you finish?
Yes, I'll be happy to go back. Yes, I didn't forget. I mean, I might have by the time we got to the end of this.
Okay.
3 problems where at least one of them is necessary. You know, you could use more than one, but one is all that's would be required. Again, you might have to do some algebra to get around having to do one of the others. 2 questions where 2 of them would be required. 1 question where at least 3 of them would be needed. Yeah.
Yeah.
Well, again, it's like I wrote it like I can do this using just 3 of them, but you might end up using more depending on,
alright.
you know what I mean? Like,
Yeah.
And those 3 ones are like the bottom ones.
yeah, that would be like a fair representation of like kind of what I would be doing. It'd be something that's nasty, but like doable. And we got to go back to this one that Mackenzie was asking about. Is that a clarification?
It was just, the clarification.
Sure. Sure.
The first 3 that says like no product or anything needed, is it usable, just not needed? Like what would be an example of those?
So
I'm sure those are like the easy ones, but
yeah, so like if we did go back and look at these review problems, like this was number 1 is something you could do that with a product property, but I didn't. Like I just did algebra to get and just use the power property to do it.
Okay.
Like, but that's one that like that would be a fair representation of something I'd put in there. Something that's like you can do this using algebra to make it the calculus easy, or you can keep the algebra easy and make the calculus hard. Kind of, you know what I mean?
Mm-hmm.
So that's an example, or like 9 is an example. Like that's one that you can just do as a single power property if you do the algebra. And if I were a little bit smarter, I could have written this one in a way that like you could have done it with just the power proper or just one property of logs, or not proper, just the exponential derivative. I didn't write it in a way that you had to do a chain rule with it, but I could have written it if I were a little bit more clever and just made that 4 to the x plus 1 instead of 4 to the 3x plus 1. Could have gotten away with doing that without a chain rule by doing the algebra similar to what we did or what I showed you on that one. Does that feel better, Tay? Okay. All right, Mackenzie. Part B, it says then we want to write the tangent line. So that's the slope is just gonna be the derivative evaluated when x is -1 and y is -1. So if I do that, I get 1 minus 2 over 7 minus 2. So that's like -1 over 5 for the slope.
So you just plug it into the final.
Yep, I just plugged it into the derivative equation, just did the arithmetic in my head. And then y minus y1 equals m times x minus x1. And when I subtract the 1 over, I'm going to have -1/5 minus 5/5, so that'd be like -6/5. And then here, I know the slope for the normal is just the negative reciprocal of the tangent line. So that's going to be 5. And I just do the same thing.
Wait, what's the normal equation? So it's n equals 1 over m tan.
Yeah, it's just the normal is perpendicular to the tangent.
Okay.
So slopes of perpendicular lines are negative reciprocals.
Okay. So just take the negative reciprocal off.
Assuming you did the first one correctly.
Right.
Does that feel okay, Mackenzie? And that should be relatively, like, the normal tangent line stuff should be pretty easy. Like, that's ostensibly an Algebra 1 problem, other than, like, you had to do calculus to get the equation to get the slope. But, like, after that, it's like an Algebra 1 problem. Do we feel any better?
Much
Can we talk about,
better.
I just want to spend a minute and talk about like the order in which we see things. So like we see some of these problems, maybe it's even better to go back and look at, or to go and look at these ones here. Right, where I have a bunch of rules going on. So let's take a look at number 1. When we look at this problem, I see one quotient rule, I see one product rule, and I see 3 chains. You guys agree with that?
So 3 chains, but they're not connected.
Correct. Unlinked chains, right? So which one needs to be done first? The quotient rule, right? Because what we're doing is we're doing the derivative of both sides, and starting off, that is a fraction. So quotient rule is the first thing that would need to happen, right? So if I call this the top f of x and the bottom g of x, I'm just going to have g of x times the derivative of f of x minus f of x times the derivative of g of x all over g of x squared, right? Now to do f of x, that's going to be a product rule. So maybe I'll call those guys h and k. So that's going to be g of x times h of x times k prime of x plus k of x times h prime of x and then minus all that stuff that we had before. Yuck. Everybody okay with that? And lastly, when I get to these ones, those all require chains, right? So a chain to do that, a chain to do that, and a chain to do that. So the chain rules are the last things that end up being addressed. Does that make sense in how we're kind of like walk through that problem? And I think going through symbolically in a problem this complicated really makes your life a lot easier. And I probably wouldn't bother with the chain rules if you can see the chain rules doing any deeper than that symbolically. Because doing the derivative of sine of 3x squared is pretty easy. That's an easy chain rule to do. It's not linked.
Could you go over number 3 real quick?
Sure. So, yeah, how many chains do you guys see here? I see 3. And then inside the last chain, I have a quotient. And inside that quotient, I have a product.
Is x times e to the x 5?
That's my product.
Could that also be a chain or
No.
no? Like if you had like couldn't your chain be like x? Like say you're outside, it'd be like x. Your inside would be e to the x
No, x is an identity function. So like if you have f of x equals x, if I do f of g of x, that's just g of x, right? So that's pure product. Does that feel okay? Okay, so if I call this one f, g, h, and then I'll call that insides k. So I'm going to have f prime. Actually, let's do this. Like f, that's g, that's h, and then that's k. Everybody's okay with that? Right? So that's the chain rule. So again, derivative of the outside, okay? Derivative of the inside, oh, need a chain to do that. So that's the g prime times h of x. But oh, to do the derivative of h of x, the inside, I have to do another chain. All right, and then you finally get down to that k of x, which is just the quotient rule with the product nested inside of it. Does that feel okay? And again, like I would write things out algebraically initially, and then just worry about the pieces, you know? Like f prime is just cosine, you know? G prime, negative sine. H prime,
So it'd be like cosine of that
secant
whole
squared.
rest of the function, and then you do the derivative of that function, which is actually the derivative of cosine, which is, I see.
So like when I'm plugging this in, I just have then cosine of, tangent of,
Right, the whole thing.
and then I have
Multiplied by negative
times, yeah, negative sine of, yada, yada, yada. You know what I mean?
Yep, it just gets smaller.
It just gets, it's big, but like,
Yeah.
oh well. Does that feel okay, guys? In terms of just like talking through how to look at these things? I saw a lot of problems with this on the homework quiz when we got to the real complicated ones where people were like, oh, I'm going to do the product rule right now. It's like, no. Like you can't just like, you see multiplication doesn't mean just do the product rule and then like plug it in later. It's like you have to kind of work from the outside in. Paul?
Could you do a problem where e is in the exponent, where it's like x to the e of 4 or whatever, plus 4x or something?
X to the e.
Yeah.
If I did the derivative of that,
Yeah.
it would just be e x to the e minus 1.
Okay. Gotcha.
Just a power rule, right?
Oh, really?
Yeah. There's nothing. E is just a constant, right? You treat it the same way you would any other constant. Is that okay? Victoria, I saw your hand.
Yeah, so remember how yesterday it was like, if there's like for number 3, if there's only like one x, like you could just do chain after chain after chain. Like, there's like 3 x's, like the x and the e, the x, and the x.
But they're all in the last parenthesis,
Okay.
which should be your cue that that's a bunch of chains until I get to that piece.
Okay.
And then I have to deal with that piece.
Okay.
Does that
Okay.
feel okay?
Wait, I can just treat e as a constant. Sorry, I can just treat e as a constant, which is like if I'm taking the natural log of x to the ex, then it would just be 0. Or I mean, it would just be x.
X to the e,
X. Yeah.
e to the x, like that?
No, where it's like e times x.
E times x?
Yeah, like that.
Well, you could do ex natural log of x, and then you've just turned that into a product property.
Okay, yeah. So e is still there. It's not. It doesn't
Yeah.
produce.
Sorry for the interruption. Any sophomores who need a picture retake, please come to the library now. Any sophomores, picture retake, please come to the library now.
Okay.
Right? You just move the constant out front and then do your product property.
Right. Yeah. I see. So if we just take that.
which just turns into e plus e ln x.
Okay.
You guys feeling all right?
Yeah, much better.
I just don't get how to know like what you do first, like the whole time.
You have to start on the outside.
Okay, so for like number 3, you did a change first,
Yeah, you have to deal with this.
and then did you deal with it?
And then, okay, so the derivative of the outside is cosine,
Right.
and then the derivative of the inside is the negative sign part. So that
Right.
tacked onto the end, then I put in the rest of that stuff, and I look at the next piece, the derivative of tangent, another chain rule, and you just kind of like plow your way through it. Mackenzie?
Number 7.
Yeah. Okay, let's number 7. Yeah, like this is just kind of gross, right? There's a bunch of chains. Shh. Okay, derivative of secant is?
Secant times tangent.
Yeah.
Right, because here there's only what?
Yep, we're doing the chain rule.
Why did you
So the derivative of secant is secant times tangent, right?
Right, but
The secant x, tangent x. And the thing inside secant is x.
oh,
And then I'll do the square root. And then we have to do the derivative of the inside, so that's 5 ln of x. Jeepers creepers. So derivative of 5 ln x squared is just that. And the derivative of the inside times the derivative of the inside.
Oh, because it's I'd say it's a change rule in the x one.
Yeah, yeah, there's like a bunch of chains in here.
wait, so you couldn't do secant x, tan x, and then do all that?
I did.
Yeah, but you separated them.
No, I did.
No, because it's
So this is f. So dy dx is equal to f prime of, that stuff is all g of x.
Yeah.
Then I did g prime of, and then this stuff is h.
No, I know that.
And then h prime of this, which will be my k.
My only confusion
And then
is,
k prime
why
of,
did you do like secant and then square root 5, and then tan, and then square root 5 off?
so the derivative of secant is secant times tangent, right?
Yes.
So if I do,
You put the x.
so I had to put the g of x into here and into here, right? So when I do f prime of g of x, I have to plug g of x into 2 places, not just one. Right?
Yeah, I just remember.
So that is this stuff right here. And the g of x is that parts. Right? Does that you can see it now?
Yeah, I understand that.
That's tricky, right? I
You
got,
couldn't do the product rule with this?
nope. There's only one x.
Okay, alright,
Can't have a product rule if there's only one x.
okay,
Right, everybody?
yes.
That's an important realization.
we didn't have that one.
If anybody needs to see me, community time today and tomorrow, both available. If you're stuck on something or if you want to talk some more about something specific, happy to see you. Makes me really excited. I'm glad to see you every day.
Like, I just